Hello, in this module we will see how to work on R to analyze data from case control study. Here we will see how to work with adjusting the covariates as a subset for case control study. We will see how to work with especially generate Kendall tau informations from case control study. One of the important area in case control study is the testing of the diagnostic tool, where new diagnostic tool is being used to find out the true positive and true negative informations that the patient is having disease or not. That is called sensitivity and specificity. So, to work with sensitivity and specificity, the emerging tool is the ROC curve. In this module, we will see how to generate non-parametric estimate of ROC curve, how to get empirical ROC curve through R. We will also see in this module. There are so many complexity for case control study. In earlier module, we have seen odds ratio and how to calculate relative breaks, but in this module, we will see some other way to how to handle case control studies data. So here we will see how to calculate the contributions of a subset of covariates, how to calculate the Kendall tau b value, how to get non-parametric area under the ROC curve, and how to compute the empirical ROC curve for a diagnostic tool. So here we will see first how to calculate the contribution of a subset of covariates to the explained relative breaks derived from the full Cox proportional hazard model. Here we will see and use the library CleanFun and library survival. As I have seen in earlier modules that library survival is useful to run the survival analysis, specifically for Cox proportional hazard model and with surv functions as well. But here we will calculate the relative breaks through Cox proportional hazard functions here, and here we will see one data set from the library called survival, and data is on cancer treatment data. In case control study, there are so many way or so many complexities are present to analyzing data. In this module, we will try to attempt few way or we will try to put some lights to on some methods to analyzing the data that will help you for further case control studies analysis as well. So let's come to their functions here. Here we are going for functions Cox PH, and this Cox PH function is available in the library called survival, and these two libraries are used here, that is CleanFun and library survival here first. And into this parenthesis given as Cox PH, we give the function called capital SURV sub functions, within parentheses again we put FU time, that is follow up time, and FU stat, that is follow up status of the patients. And these things has been modeled for the covariates called age, and that is mentioned as small AGE. In addition to the another covariates considered here as a residual.ds, that is residual disease presence or not, and after that RX is assigned as that what kind of treatment is given. Here if you go to the library survival, and after that if you call the data ovarian, we will get the details features about the factors or covariates mentioned here. We are not going into details about these factors here, but in addition to the RX, we also consider another factor that is called ECOG.ps, that also available in the data set ovarian. And after that we had assigned that data equals to ovarian, and the whole functions programs is assigned to ovarian fit. Now our intention is to find out the relative breaks, as I have mentioned in these earlier modules. The relative breaks is given the idea or is the proportion of disease among exposure with respect to proportion of disease among non-exposure, and we have seen the function to calculate direct relative risks. Here we are calculating relative risks with respect to covariates. Here it is to be mentioned that here the covariates are considered are age, recid.ds, rx and ecog.ps. So 4 factors, 4 covariates are here, and 4 factors having, among these 4 factors except age, 3 factors like recid.ds, rx and ecog.ps is having categorical variable, and they are also the like recid.ds is having discrete variable 1 and 2, rx also having discrete variables like 1 and 2 like given treatment, and ecog.ps also having discrete variable like 1, 2, 3, 4. So here the base numeric base value, like if in case of recid.ds numeric base value 1 is considered as a reference category. In case of rx also 1 is considered as a reference category, and in case of ecog.ps also this reference category is considered as 1. And now we are coming to the numerical variable, that is age. It is, since age is considered as a continuous variable, so here the interpretation about relative risks will be with respect to smaller age group, what is happening to the higher age groups. Now when we are calling that functions called Cox PH ERR, that function is available into clean fund library, not in the survival library. This function is available in clean fund. When we are putting this Cox PH ERR, that is expected relative risks, and within parenthesis when we are putting ovarian fit and putting enter, then as a result we are getting the expected relative risks value as a 0.68 with standard error with 0.125285. So here we will consider only 2 decimal place. So here if we consider the relative risks value is 0.68 with its standard error 0.12, this standard error can be used to calculate the 95% confidence intervals with these relative risks. So as a measure we can see that the individuals having relative risks for dying is 68%, 68.41% for those are having higher age groups. Those are having treated with residual with 2, and those are having treated with RX2, and as well as having higher performance status. This is the basic statistical inference about that. Here for illustration we have considered 4 factors like age, residual disease, RX and ecog.ps, but here we can consider only one factor also like RX. If we consider only RX as a right hand side and left hand side consider as a serve, a few time and a few status, then we can find out what is the relative risks of getting die by those are treated with RX2 with reference to RX1. The same thing is happening again when we are putting Cox PH ERR within parenthesis ovarian fit comma C1 to 4, that is giving us the for first 4 individuals relative risks, and it's saying that these first 4 individual relative risks were quite lower in comparison to all individuals, and it's saying that expected relative risks is coming 0.40 with standard error 0.19. So this standard error can be used to getting the confidence interval of the estimate of the relative risks. Now we will go to this next way to calculate the next functions. Now we will go to next data that is also available in this library called survival. That primary biliary cirrhosis data is used here. We are not going to show the whole data set. You can call the survival library, and after that call the data PBC. Here the first 5 individuals data we are showing here with the snapshot taken from the R, that PBC 1 to 5 within comma and completion of the bracket. is showing that the first 5 ID as 1 to 5, time was like 4500, that is observations time of those individuals, and status is giving as a 2, 0 and 1. So here also the 0 present that they are censored, and 1 present they died, and 2 present they died due to some other reason. And again treatment 1 and 2 given, what kind of treatment is given present by 1 and 2. Age also given in 50, like for the first individual is 58.76, second 56.44, like that. Their sex is mentioned as A for M, so A for female and M for male. Now the other biochemical parameters like elasticities given as presence or absent given as 1 and 0. So if it absent then represent as 0, if it present then represent as 1. Hepatological parameters is given as again 1 and 0. So hepatology, presence or absence, spiders, another parameter again given as 1 and 0. Edema and level of edema was given as 1, 0 and 0.5. Bilirubin level was also given 14.5, 1.1, like second individual, third individual 1.4. Cholesterol measurements also given here. Another variable albumin, next one copper, next one alkyne phosphate, AST, triglyceride, platelet, protein, stage, all these variables are considered. So the meaning is to this is the typical kind of data set present in any case control study. So now question is that how these factors like all these biochemical parameters contributing towards their long survival or not, that need to be find out. So here in this data set we will select few covariates or few factors from this data set, and we will check how to get the relative risk estimations from this data set. So we are going for next slides. Before that, this is the summary of these parameters. Again, summary of PBC when we put we are getting this summary information about the all variables covariates here. This is again snapshot taken from the art studio, and this ID, time, status, TRT, age, sex, acidities, hepato, spiders, edema, bilirubin, cholesterol, albumin, copper, alkyne phosphates, AST, triglycerides, platelet, protein, and stage is given here. So this you can see this what is the minimum and maximum observation for each variable, and what is the mean and median measurement for each variable. I'm not going in details onto that. Now we'll go to see these functions to getting the relative risks. So here these functions to contribute these survivals on the covariates. So again we are calling the data PVC, and after that PVC fit, and use the Cox pH functions. Again like same other earlier functions where we again putting serve of time and status 2 is considered here with treatment and log of copper, so comma PBC, and as a subset those are treated with more than treatments coded as 0, 1 and 2. So those are quoted more than 0 is being considered here, and copper again those are treated more than 0 copper were considered as a subset functions here. So now we are trying to put these measurements as a plotting. So we are putting the plot of log PVC of copper, those are having treatment greater than 0, and copper also greater than 0, and another axis we are putting PVC of time. The same condition is given here, PVC of treatment greater than 0 and copper greater than 0. On the type of line we are putting into the common, so PCH. There are so many options. Here we are putting O and X options, and when we are putting the X lab, so as a X lab we are putting the log of copper value, and Y lab we are putting the survival times. Now next slide we will see the graph. Before producing the graph, we are also using the functions Cox pH quantiles to get the quantiles informations, quantiles estimates into the graph only. Not only that, only the quantiles, we are also putting these quantiles with another color for 75% quartile. So first Cox pH quantiles will give us the first quantiles, and 75% quartile, or that is third quartile, will be obtained by second function, that is Cox pH quintiles on the same data. That is, in both case, into the Cox pH quintiles we have used the PVC fit, and we are putting these functions, we are giving with different color, and for the second one we are putting color equals to 2, and since the first one we didn't put any color, so it will give us the by default color. Again we put the Cox pH quantile, PVC and PVC, again we have seen the earlier how to put the Cox pH. Let's see the graphs. This is the graph. Since we didn't put any color for the first quantiles function, so we are getting by default the black color, and for the second that is for 75% quartiles, we put the red color, color equals to 2, COL equals to 2, so we are finding as a red color. The quantile distributions we can see here, where the quantiles are lying here, and again the scatterness of the log copper with the survival time can be seen here. That is basically obtained by the model fitting criteria here, and we can see that there is not any specific tendency among log copper with the survival times. It can be represent those who are having higher log copper, they are having higher survival times. That can be somehow managed from these graphs, but obviously any specific tendency not been found here. Now we will go for next objective, that is to obtain the Kendall tau estimate, and here the Kendall tau is Kendall A and Kendall B. Here we will go for Kendall B estimates. This to mention that in any case control study, our intention sometimes becomes to find out the relation between factors. This is not the direct link up to our establishment with these covariates with response variable here, but when we are trying to find out or explore relations between two covariates, then we go for Kendall tau B estimates. Obviously correlations, that is Pearson's correlations coefficient, is suitable for that, but the limitation of Pearson's correlations coefficients is that when you have to get the huge number of sample size, but in case control study generally sample size becomes very less. In that case, Kendall tau becomes more useful than Pearson's correlations coefficients. However, both having the same characteristics. Here the Kendall's tau B is having range between -1 to +1. So if we are planning to find out the relation between two factors, like here you have seen this platelet and albumin, or platelet or alkyne, and if you want to find out the relation between two continuous variable and finding that Kendall tau B value coming to 0, then we can interpret that there is not any relation between these two variable. If Kendall tau value coming near to 1, then we can interpret that there is a strong associations between two variable, whereas Kendall tau value comes near to -1, can be stated that there is a negatively association between two variable. So but here we are not using any specific variable to illustrate you. We are using two variable, that is x and y, that is generated from normal distributions with 1000 normal distribution data x and 1000 normal distribution y has been generated, and we want to find out the between correlations between these two variables. So see here, x has been obtained from R of norm 10,000. If we want to put the only simple Pearson correlations, then if we put COR within parentheses x and y, then we will get the Pearson's correlations coefficients value. But here in this library called CleanFun, we are using the core of COR with x and y, and after that putting method equals to k within inverted comma, and that giving us that the Kendall tau beta estimates, and here we are getting the value as a 0.49, so it can be stated that there is a positive correlations between x and y. So that can be again used in other parameter also, other covariance parameter also, we'll see in future. And there's a command giving, and y is obtained x plus R norm 10,000. So obviously there is a there must be good relations between x and y. Now we will go to next objective, that is to find out the area under ROC curve. This is to be mentioned that ROC is a production of two parameters, indicators specifically, that is, one is sensitivity, another one is specificity. Sensitivity is used to find out the true positive value among the individual. So sensitivity is specifically a diagnostic tool to detect the individual having how many positive cases, and the sensitivity as much as high, it can be stated that the diagnostic tool is as good as to detect true positive value. It don't consider the negative value, and as well as this diagnostic tool is when it's find out as good as false true negative value, basically, then it's called good specificity value. So it is to be expected that a diagnostic tool having wonderful specificity, that is 100% sensitivity as well as 100% specificity. So now there is a cutoff between the sensitivity and specificity. So when we are proceeding in a trial and we are trying to find out that how the diagnostic tool working, and then this cutoff between sensitivity and specificity give us the informations how this diagnostic tool perform. So that cutoff area can be obtained by the ROC curve and is stated as the area under ROC curve. So as much as the area under ROC curve is there, the diagnostic tool can be inferred as the best diagnostic tool. Here we also, as an illustration purpose, we are generating data, and from x as a normal distributions as R norm of 100 plus g, and again g is taken as the replicates of 1 to 50, and y again considered as R from R normal with 100, again g, and z is again distributed obtained from the normal distribution. So here we are having three variable x, y, z, and most of them and three of them highly correlated. Now see that functions, that is roc.area.test, and when we are putting the c bind of x, y, comma z, so we are trying to find out here the relations between x and y for truly detecting between sensitivity and specificity with and the marker 2, as a result we are getting two markers with AOC as 0.73 and 0.82. so it's a measurement of sensitivity. First measurement is coming as sensitivity measurement is coming as a 73.48%, whereas specificity measurement coming as 82.04%. So now when we are putting this test statistics, is obtained that there is not any significant difference between the two diagnostic tests. So again this can be again used in this another in real life scenario, these functions, and this function is available in the ROC. This function is called roc.area.test. It is available in this library called CleanFun, and it's open source software. R is available to analyze this area under curve. Now we will see this another one, and that is relations between these three markers, that is x, y, z. Now again this relation is coming with significance p not significant p value, that is 0.23. so it's again saying that both three are having equal information, so they are highly correlated. So these three markers is having working in better same way. Now in last we are trying to find out the generate new variable, that is y1, and y1 is a productions of y with addition to this 0.75 with the g, and when we are putting x with y1, we are getting this two markers AOC curves is coming 0.7348 to 0.938. The test statistics value is 3.714313 with p value highly significant. So now there is a significance difference between these two marker value. Now we will plot these ROC curves here. Again the earlier functions we have used, that is to generate the x from the normal distribution, that is R norm 100 with G, and y R norm 100 with 1.5 with G. And again we are using the function ROC.curve with x comma g and putting plot of O, and these lines are given here. Now we will see this is a simple functions here, and this is result empirical ROC curve. So first lines, the red lines are for the sensitivities, and the black lines is for the specificity, and the common area between these two line is started to touch in near to 0.1, and again they started to touch in 0.9. So into this area that can be called as AOC area specifically, and this curve is called the ROC curve, and here the x-axis showing the false positive rate and the y-axis showing the true positive rate. So when we are having in a case control study and we are trying to find out the diagnostic methods are doing, how they are doing with each other, then we can plot the ROC curves with these functions. End of this, here we have seen how to generate relative risks through Cox-Ph functions. We have seen how to get the idea about the Cox-Ph with another data set. We have seen how to get the Kendall tau b estimates from the covariates, and we have seen how to get the ROC test value and generate the AOC value as well as empirical ROC. Now here we have seen how to generate Kendall tau b from case control study data. However, here we have used normal distributions to generate data, and after that we have used Kendall tau, but in real case control data also we can apply these functions mentioned here to obtain the Kendall tau value. In this module we have also seen how to work with covariates adjustment for subset, how to get relative risks in case control study. Here we have also seen how to work with new diagnostic tool and as a product generate the non-parametric estimate of ROC curve. Here we have seen how to work with R to generate empirical ROC curve.